Yeah, each of these parts can become different things.
These ones are the same.
Oh.
You
You can write U two times, but they will not be the same thing. Yeah. All right, I think it's time to get started. We do have homework tonight. I guess most people know that. Was the homework too long this time? I wasn't sure. No, nobody complained, so all right, great. I hope it's not too long. So we will have our usual test on Friday. A little reminder, I don't know if you've been paying attention to the calendar, but our next exam is next week. Did I say we'd have a test on Friday? It's a quiz on Friday of this week. Sorry, I mixed it up. This week is a quiz based on the homework, as always. But then next week, we are going to have a usual homework assignment. But next Friday is our next exam day. So, I think you know what to expect on the exam. But the exam does not reach back and do old topics, so it will cover only the stuff that we've done since our first exam. I'm not sure I recall exactly where the cutoff is, but I will figure that out, and we will discuss the test in more detail next week. Anybody have any questions about the test for now? All right, great. Let's continue. I gave you like a 5-minute introduction to stack machines last time. Let's talk about stack machines. This is our next big topic in terms of types of machines. A stack machine is a kind of machine which can use a stack for its memory. A stack, as far as memory goes, is a fairly simple kind of structured memory in which you are only allowed to access the thing on the top of the stack. So if the stack said something like A, B, C, D, I think this is maybe exactly what I wrote last time. You are only allowed to access the top of the stack. You think of it as like a stack of books or a stack of pancakes or something. I don't know if a stack of pancakes is a good example, because you usually cut through all the pancakes when you're eating a stack of pancakes. Imagine a stack of pancakes in which you have to eat them one at a time from top to bottom. Is there a better food analogy I can use?
Like a Pringles can?
Like a can of Pringles. Yes, that's a better analogy. Or I was thinking like a kebab skewer. You have to take the one off the end first. Yeah, you could bite it like this. That's true. All right. Yeah. Yes, a can of Pringles. There are two operations that you can do on a stack. You can remove the thing on top, or you can put a new thing on top. So the removing on the top operation is called a pop. So going from there to there, you pop the D. The D was on the top, and then it gets thrown away. Or you can put a new thing on the top. I think I drew exactly this last time. Say an X. This is called a push. Push X onto the top. All right. Now, this like drawing the stack as like vertical towers, we are basically never going to do this. It's just a pain to write things in that way. We are always going to write the stacks as strings with the top of the stack being the left end of the string. So I'm going to write these stacks like this. All right, where this was a pop the D, and then if I push a X, it looks like X, C, D, A. All right, so sort of when I write a stack that way, just because it's a pain to write these vertical tower things, the top of the stack is the left end. All right, that's how we're going to write our stacks. Okay, and the machine, the idea of a stack machine is it can read the input string one letter at a time, just like any other of our machines. And as it reads the string, it is allowed to modify the stack according to certain rules. We don't really represent these with diagrams because, as I mentioned at the very end last time, a stack machine, in theory, can have infinitely many different possible states. That's because the stack is allowed to grow as big as you want. And so there's more than finitely many possible configurations that the stack can be in. There are infinitely many possible configurations. All right, here's an example of how we are going to represent a stack machine. We don't have a diagram, really. It just tells you what are the rules for when I read this kind of letter, what happens to the stack. That's the whole deal here. So it's going to look like this. Read, pop, push. Every stack machine will be described by a chart of rules like this. And I'm going to give them numbers in this case, although often we won't give them numbers. So rule 1 says read A, pop S, push SX. Rule 2 says read B, pop X, push epsilon. Epsilon, as usual, means the empty string. Rule 3 says read epsilon, pop S, push epsilon. So what these rules mean, if I were to give like a narration of what that first rule means, it means if I read A in the input string, I can pop S and push SX, right? The idea of a stack machine, remember, is depending on what you see in the input string, you modify the stack in a certain way. And what the first rule says is if you see an A on the input string, you can modify the stack in this way. You can pop S off the top and push SX back onto the top, all right? The second rule is similar. The last rule is something like an epsilon transition. If I read epsilon, that is, the last rule can happen whenever you want without reading any part of the string. So I'll say without reading any letter, this is like an epsilon transition. I can pop S and push nothing, right? This will just throw away something from the stack and not replace it with anything. Yeah?
So, how do we know when to read the epsilon?
Yeah, how do you know when to do each step? The answer is the stack machine is kind of like an NFA in that when you read a particular letter, you may have several choices of what you're allowed to do next. Just like an NFA, which can have, say, 2 outgoing arrows labeled with the A. The answer is you can do either one, sort of whichever one works. And you can do this epsilon step whenever you want. All right. Let's try to decide, or I have to tell you the basic setup about what does it mean to be accepted or rejected on a stack machine. The idea is our stack begins with S. So this is always going to be the case. The stack always begins with the starting stack symbol, which I'm always going to call S. And you read the input string, and a string is accepted if we can read the whole string, one letter at a time. And end with an empty stack. That's kind of your goal, and that's what it means to be accepted. If you can read the whole string and finish reading the string and end with an empty stack. If the stack ends up being empty, the string is accepted. And if there is no way to get to an empty stack, then the string is rejected. All right? That's how it works. Let's just try an example. So this particular stack machine here, I would like to know is, how about this? AABB accepted? For this particular stack machine, I'm going to maybe copy it down here just because I don't want to scroll away from it. I'm going to try to make a little chart here of what happens as we read the string. So my input, I have to keep track as we go letter by letter. I have to keep track of what the stack looks like from one step to the next. All right, so when we begin, my input string is AABB, because that's what I said. I'm trying to decide, is AABB accepted or not? And when we begin, the stack starts with the stack symbol S. This is just always how you begin, with just S on the stack. All right, so this is, I'll give a little commentary on the side here, although usually we're not going to write out this much detail. All right, next, we read the first letter, which is a A. So my input, I'm going to, just so that I keep track of where I am, I'm going to kind of cross off. In the first step, I read the first A, all right? What happens to the stack? What happens to the stack? When you read an A, you pop S off of the stack and you push SX. So can someone say, what will the stack look like after that step? It will look like SX. I think I heard a whisper in the wind. You throw, the stack right now has S on it. Pop that, which means you throw away the S, and then you replace it with SX. So this stack will now say SX. All right, so this was step one. I did rule number one there, right? We read the A. We throw the original, the stack used to have S on it. We throw the S away, and then we replace it with SX. That's what the pop and the push mean. Okay, next letter. Next letter in the input is A. So we're going to have to do rule number one again. So I now my input looks like I read the first two letters, and now just BB remains. What happens to the stack now? We throw away the S that used to be on the top, and then we replace it with SX. So can someone say, what will the stack look like now? Yeah. SXX. Right. The old S got popped away, and then it gets pushed back. You replace the old S with SX. All right, that was, again, rule number one. Okay, next. The next letter to read is B. Now, I will say, at any point here, you could have decided to do rule 3. I just didn't. Now, you might say, maybe I could have made the string get accepted if I used rule 3 at some point. Actually, it's definitely a bad idea at the beginning, because then you would have exhausted the stack. You want to get down to an empty stack at the end of the string. There are certain amount of sort of different choices that you could make from step to step. I am making these specific choices just because I know this is going to work out in the end for this particular example. Is that what you're going to ask? Yeah.
Which way is the head of the stack?
The top of the stack is on the left.
So when you push SX, you put X first, and you push X.
When I push the SX, it's like this S turned into that SX.
Okay, so the left is the
Pushing, the top of the stack is on the left, and you push everything onto the left.
That means you push X first, and you push X.
Yes. Yeah. Or you stick them together, push them together. Yeah. Okay. What next? I'm going to do rule 2 next, because the next letter I see is a B. So, no, actually, rule 2 is not allowed right now. You can't do rule 2 because it involves reading B and popping X, right? And I don't have X on the top of the stack here. So rule 2 is not allowed to do at this point because it requires a pop X, but I can't pop X because the top of the stack is not X. Rule 1 is not allowed because it requires you to read an A. So actually at this point I must do rule 3. That's the only option. It says read nothing, pop S off the top of the stack, and replace it with nothing. So actually after doing rule 3, it now looks like this, just XX. I did number 3 there. Number 2 was not allowed there because it involved popping X. All right. Now I can do number 2 next. because x is actually on the top of the stack at this point. So we're going to do number 2. Actually, I'm going to do number 2 twice, but I'll do it one at a time. Number 2, read the next b, pop that x, and replace it with nothing. That was number 2. And then I read the final b, pop that x, replace it with nothing. The stack now is empty, and I'm done with the word, and so it is accepted, right? We read through the whole string, and the stack is now empty. It is accepted. All right? Any questions about that? As usual, all of these things, takes a little bit to get used to doing a stack machine, but we'll get there eventually. We just need to, today we're just going to try a bunch of examples. Maybe I'll, just so that I don't have to scroll this away, can we try another string over here? So this one was AABB is accepted because I got down to the empty stack after reading the whole input string. All right? To be rejected means, it's a little harder to show that something is rejected, but it means that there is no possible way to read the whole string and get to an empty stack. Let's try, I happen to know this word, ABAB is going to be rejected. Let's try that one. I'm going to try and do it over here. So I began with ABAB on the input and S on the stack. This is how you always begin. And for my first step, I'm going to do rule number 1. Now you can do rule number 3, but you'll become stuck immediately. If you do rule 3 here, it will empty the stack, and then you'll have A on the front, and then you'll have nothing to do. So rule 3 is a dead end from this point. So I'm going to do rule 1, which reads at A, pop S, push SX. So it looks like that. That was rule number 1. Next I see B, which means I feel like I should do rule 2, but actually rule 2 is not applicable right now because rule 2 is a pop X, but I don't have X on the top of the stack. Can we do anything at this point? I see somebody showing me the sign. 3, yeah, you can do rule 3 at this point. It's the only thing you can do. Your only option is to do rule 3, which is read epsilon, so I just keep the input string like it is, but then pop S and replace it with nothing. So now I have X on the front. That was rule number 3, all right? From here, I believe our only choice now is rule 2, right? Because it requires a B on the string, which I have, and an X on the stack, which I have. So we can do rule number 2. Rule 2 will pop this X and replace it with nothing. That was rule number 2. And now I think we are just completely stuck, right? I have an A on the input, which suggests maybe I should do rule number 1, but that requires a pop S, which is not possible. The only alternative would be maybe doing the epsilon rule, number 3, but that also is not possible because that needs a pop S. So here we are stuck. And there was no other choices we could have made earlier that would have made this actually go all the way through. So that means ABAB is rejected. Right? That's how it goes. Any questions about that? This is a standard example of a stack machine. Now, this is a little cumbersome to write things in this way. Actually, we are usually not going to write it in this style. These stack machine derivations, we're going to write them like this. Really, all that matters, think about this whole chart here. What is essential from one step to the next? I would say what matters is what we have left on the input. The input kind of shrinks every time, or maybe it stays the same if you're doing an epsilon. Every time the input string is shrinking one by one, and the stack is changing. Sometimes it grows, sometimes it shrinks, right? That really is all that matters. So this one on the left, the way we're going to write it is with a bunch of pairs like this. You begin with the full input string, followed by the stack symbol S, and then our book, just because the author of our book likes to use different shaped arrows for everything. So in a stack machine, they write the arrow, which has the little post on the left side. I don't care if you follow exactly the arrow conventions in the book, but I'm going to try to as much as I can. The next step here will be written like this: A, B, B, comma, S, X. And then the next step is just B, B, comma, S, X, X. And sometimes they're going to, in the book, sometimes you'll see they label the steps with little numbers. The numbers refer to which rule you used when you did that step. Although it's not always essential to write those numbers down. All right. Next was rule number 3, which made it was an epsilon, so my input stayed as BB, but the stack became XX. That was rule number 3. All right. I'm just going to write out all the steps here. Then it became B, comma, X. That was rule 2. And then finally epsilon, comma, epsilon, which was rule 2. All right. So this is a more compact and more, just a nicer way to write that whole process. All right. So what we have here is each pair is actually there's a term for this, is they call this an instantaneous description. You think of each of those little pairs represents sort of a snapshot of this machine while it is doing its computation. They are called an instantaneous description, also written ID, instantaneous description. So what we've done here is like writing a sequence of IDs. And what it looks like is, something, comma, something. The second thing is just the stack. And then the first thing in each of those pairs is the piece of the input remaining to be read. Remaining to be read, right? That's how the pairs go, just so that it's clear. And the idea is X, if you have some string, X is accepted when we can do a sequence of IDs which begins with SX, a bunch of steps, and eventually, what are we looking for at the end to be accepted? You can see that. Yeah, epsilon, comma, epsilon. So the first epsilon indicating I read the entire input string. The second epsilon indicating the stack becomes empty. All right, so this is kind of the goal when you're writing a stack computation. You have to start with your whole string followed by S, and your goal is to do those rules in some order to get down to epsilon, comma, epsilon. If that is possible, it's accepted. And if this is not possible, it's rejected. That's the idea. All right. Can we talk about that example that we just talked about? Did anybody get any kind of sense for how this stack machine works? Can you tell me what are the strings which are accepted on this stack machine? How do you, of course, this is what we call the language of the stack machine, would be the set of all strings which are accepted on this machine. I feel like looking at this computation is instructive, this first one here. What I see is basically whenever you see an A, that causes the stack to gain another one of these big X's. And then at the end, you cross the X's out every time you see a B. Any thoughts? Yeah, this is A to the N, B to the N. As you're reading the A's at the beginning, the stack is kind of storing the information about how many A's did I see. It adds another X every time. And then at some point you reach the middle, you reach the end of all the A's. At that point you pop the S off, and then you read each B and cancel an X every time. And all those X's which built up on the stack get crossed off one at a time. Yeah?
The number of A equals to the number of B.
In this case, I believe they have to be all the A's first and then all the B's. Yeah, he just asked, could they be mixed up, but the same number? I think it's because of this step here. Before you cancel the x's, you have to do this to get rid of the s. But then after you got rid of the s, you're not allowed to see any more a's here. Yeah. All right, so that one right here, in this case, the language, that is the set of all strings which are accepted, is a to the n, b to the n. All right? So one thing this tells us immediately, a stack machine is more, you can do things on a stack machine that you can't do on an NFA, DFA, right? Because that is not a regular language. So a stack machine, in theory at least, is capable of doing some non-regular languages. Yeah?
Could you please scroll down all the pairs again?
Yeah. Is that what you're looking for?
Yes.
Yeah, this is a translation of that stack derivation into the IDs. All right, let's try another example. He's writing furiously. Can I do this? Can you still see him? I got another example. I keep on writing things slightly differently. There is no other way that we're going to write a stack machine. It's always going to look like a little chart that says read, pop, push. All right, I scrolled forever. Let's try read A, pop S, push X. Rule 2, read B, pop X, push Y. 3, read B, pop Y, push S. And 4, read epsilon, pop S, push epsilon. All right? You know, the usual question is, what's the language of this stack machine? And if you don't have any idea how to get started, I would suggest just like try out some different strings and see what happens. Let's try, how about ABB? What does it look like? So we begin ABB, comma S. And then you do whatever rules are appropriate. Often there's only one possible thing to do. Actually, in this particular example, you could do Rule 1 or Rule 4, although I don't like this. I don't like the feeling of Rule 4 just because it's going to empty out the stack immediately at the very beginning, which is usually not a good idea. So I'm going to start with Rule 1. Read A, pop S, push X. So when I read A, that means my input string becomes BB, right? The old way of writing it, I would like cross the A off, and you can do that if you want to, but we're just going to omit the A. This input string is now BB, and then what's the stack going to look like? X, right. The S got popped, and then it's replaced by a X. Okay, what next? BBX. Again, the epsilon transition is not allowed in this configuration because I have X on the top of the stack, not S. I can do Rule 2 or 3, I suppose, to read a B, but actually 3 is not going to happen because I have X on the stack. We must do Rule 2 at this point. That one I just did was Rule 1. Like I said, we are not always going to write the numbers there. Once you get used to this, it's not really necessary. So I'm going to do Rule 2. Read that B. So now the input string is just a single B. And then pop X, push Y. So the stack becomes just Y. All right. Next rule, I think you have to do Rule 3 at this point. Get rid of the B. My input string is now epsilon. And my stack is now S. And then our only choice is Rule 4, but Rule 4 actually is going to do it for us, right? We read epsilon, which keeps the input string as an epsilon, and then pop S, push epsilon. It's like that. So this is accepted. Accepted! Exclamation. All right. How about, let's just try one. Let's try AAB. What happens with that? AAB and S. Sorry, I scrolled some of the words. I'm going to zoom. In this one, this actually is going to be rejected, but we could try starting with rule 1. It would go to AB comma X. But I think I'm stuck immediately now, right? Because I have to read A, but the stack has an X on it. So this here is stuck. We could have, just to exhaust all other opportunities, the only other thing we could have done was the epsilon move, which is rule 4, which would have made it AAB comma epsilon, and then we're stuck again at that point because you can't, because the stack is empty. So either way, this is rejected. All right. Either of the two moves we could have done at the beginning is not happening. So actually, I think this string, and notice that we didn't even get to the B yet, right? Really, anything that begins with AA is rejected, right? We can tell that because you can't even get past the AA without getting stuck in this case. Can we say in any kind of more specific terms what is accepted or what is rejected? You got an idea?
Is it A, B, B to the N? So
A-
repetitions of A, B, B.
Yeah, it is A, B, B to the N. That's right. Do you have some explanation? Can you say what makes you feel that way? You can tell us about your feelings. Is this a safe space? It's kind of hard to say, but that is correct. I would say something like we started with ABBS, and that brought us down to epsilon comma S. It's as if you had ABB on the front of your string, you can do certain steps to just remove that from the front of your string and end up with an S here. Like if we had done the same steps, if we'd started, for instance, with ABB, comma S, we could do those same steps in that same order, and it would get down to just ABBS. It would cancel the first ABB and then the other ABB. But then you can just do that again and cancel the rest of it. Another.
Does it always have to start with S?
Yes, when we do a stack derivation, we always begin the stack with S on it. Yeah. Here's another, maybe a little bit fancier way of thinking about this particular stack machine. I think you will notice, just if you look at the structure of the pops and pushes, that this stack always has one thing on it. Like it's not ever possible to make the stack look like XXX, right? Because all you can do is pop one thing and push another one thing, all right? Like this previous example, it could grow because of this rule. The stack can grow. But this one, actually, this stack never grows more than just one thing. And it can become empty, but it can't get any bigger than one thing. The fact that the stack, if you think about it, isn't there only like 3 or 4 possible things the stack could be, right? It could be S or X or Y, or it could be the empty string at the end, all right? That suggests that this particular stack machine actually only has finitely many states. It can only have those 3 different possibilities for what the stack is. So this particular stack machine, this is not always true, but for this one it is true. This stack machine can be converted to an NFA because it only has a few possibilities for what the stack can be. And in fact, you can write the NFA very much like that stack machine. It has a state where the stack is just S. And if the stack is just S, you can read an A and turn the stack into an X. So I put an A there. If the stack is X, you can read B and turn it into a Y. If the stack is Y, you can read B and turn it into X again. And the fact that that epsilon transition on the stack machine basically makes S an accepting state. It means if you end everything, if you end up in S, then it's accepted, right? This is an equivalent NFA. And from here, it's clear to see that what he said before is correct. The language of this is ABB to the n, right? Because you can go around that circle as many times as you want. The language is, or like as a regular expression, it's ABB star, right? Or as a set, ABB to the n. Usually that's not possible to convert a stack machine into an NFA like that, but that particular stack machine is simple enough that, that you can convert it into an NFA. All right? Let's try one more example, and this may do us for the day. This is a quite a bit fancier one. How about this? This time I'm going to give you the language, and then we'll try and make a stack machine for that language. This is the other type of typical homework question about these things is like, I show you the machine, you tell me the language, or it could go the other way around. I show you the language, you make a stack machine. How about this? X in AB star such that the number of A's equals the number of B's. One of my favorite non-regular languages. It's like A to the n, B to the n, but it could be in any order. This was the one from last time we did a grammar for this, which ended up being quite complicated. As a stack machine, it's not as bad, I think. Although you still have to have kind of a cute idea for it. And here's my idea for this stack machine. My stack always looks like, my stack will always look like something like XXXS or XS or YYS. It's going to have X's and Y's and S. And I'm always going to leave the S on the bottom of the stack, which is different from the other one. We always left S on the top, but I'm always going to leave the S on the bottom. And these X's, so X represents one extra A in the string. The idea is the stack machine, as it reads the string from left to right, it has to keep track. Is there the same number of A's and B's, in which case it should be accepted, or are there extra A's, or are there extra B's? All right. Each X represents one extra A. So if you see this on the stack, it means the string that you've read so far has 3 extra A's in it. 3 more A's than B's, as we've read the string so far. This would mean it has 2 more B's than A's, as we've read the string so far. So X represents 1 extra A, Y represents 1 extra B, all right? And it'll be accepted if we get to the end with just a S on it, and then I'll have an epsilon to throw the S away at the end. This is the idea. So actually, before I give the rules, I'm going to tell you what a typical derivation might look like. A typical derivation would be something like if I had, let's say, A, B, 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 A, B, A, A. That's a kind of complicated string, but I'm just trying to make it interesting enough to make the derivation interesting. So what we're going to do, I'm just going to, and this is sometimes helpful when you're trying to create a stack machine, I'm just going to write down what the derivations should look like, and then I'll turn those into the rules. So what it should do is when it reads the A, it should put an X on top of the stack. So this should become BBB, ABAA, XS, right? Because I read that first A. It means among all the parts of the string that I've read so far, there's been 1 extra A so far. All right, next letter I see is a B. When I encounter a B, that should kind of cancel out the extra A that I used to have, because this next B now equalizes the fact that I had an extra A. So the fact that I read a B next, I'll cross out that B. I got BBA, BAA. We'll just cancel the X on the front of the stack, right? The X represented the fact that I had an extra A, but now I've read another B, so that should cancel out the extra A that I had before. All right? Next, I read a B, which is now an extra B. So I'm going to put a Y on top of the stack. YS, right? Next, I read a B. I'm going to put another Y on top of the stack because I have now 2 extra B's that I've read. So it'll say A, B, A, A, Y, Y, S. All right? Next I read an A. What should I do with the A? Well, if I had extra B's from before, the A should cancel out one of the extra B's. So when I read an A, I should pop Y off and cancel it out. So now it'll say BAA, YS. All right. When you read a B, you should add another Y because the Y's represent extra B's. So next I will go to AA, YYS. And then as I read those A's, they cancel off the Y's. So it'll say A, YS, then epsilon S. And then I'm going to have a special rule which just kills the S at the end. Epsilon, epsilon, and it'll be accepted. All right. This is the strategy. A little complicated, and you have to have this idea about you use X's to remember extra A's, you use Y's to remember extra B's. All right. But anyway, given that that's the derivation, can we translate that into a set of rules that that describe exactly what I was getting at for all of those things? Let's see. I got read, pop, push. So maybe I'll just sort of start off. If you read an A, there are, I'm going to make 3 different rules for what to do with you. If you read an A and there's an S on top, or if you read an A and there's an X on top, or if you read an A and there's a Y on top, right? Those are the 3 different kind of tops of the stack that you could encounter. Can anyone say, what should I push? If I read A, pop S? I think I did that once in this XS. Yeah, is that what she said? I think that's what somebody said. Right here, I did that rule. I had S to begin with. I read the A. Now, it looks like all I did was insert an X. Every step, though, has to involve a pop and a push. So in that case, the way to write that is I pop S and I replaced it with S, XS. All right. Yes?
Why can't you put an epsilon for the pop, instead?
Yeah, so this is a technicality. In a stack machine, you're not allowed to pop epsilon. Okay. That's a stupid answer to a good question, but yeah, this is just a part of the true definition of a stack machine, which I haven't actually said. We're gonna, I guess next time we'll give there is a formal description of a stack machine, and you're not allowed to pop epsilon, even though that it doesn't actually change anything if you do allow that or don't allow that. But for whatever reason, in our book, our stack machines are not allowed to pop epsilon. You are allowed to push epsilon, and you are allowed to read epsilon, but not pop. I'm not sure why our author decided to do that. Anyway, what about read A, pop X? What should I push? I'm not sure that ever happened. XX, yeah. If you are reading an A, you need to put a new X onto the stack. So it has to look like pop X, push XX. And what if I'm reading an A and there's a Y on the stack?
Epsilon.
What do you say?
Epsilon.
Epsilon, yes. I thought he said XY, which is wrong. It's epsilon, yeah. The Y represents, the meaning of the Y is that there was an extra B, and the idea is if I now read an A, it equalizes that extra B, and so we don't need the extra B anymore. Yeah, great. What about the others? I'm going to have to scroll, unfortunately. How about when I read B's? Again, there's going to be sort of 3 different things to happen while reading a B. BS is going to be YS. That's because a B represents, or a Y represents an extra B. And the S means kind of like everything has been equal up to this point. So if you see a B, that means now we have an extra B. What do you get for a B and an X? Someone shout it out. Yeah, epsilon for that. Because X represents extra A's and a B cancels it out. BY gives you a YY. All right. And then finally, there was one other rule that I used, which is only used at the very end here, to do that. And it's just epsilon S epsilon. All right. Yes?
How do you even before doing the rules or starting the derivation, how do you figure out what you're doing?
Yeah, this example is kind of difficult, and I think you're referring to this whole thing, how did I come up with this idea? The answer is you just have to have an idea. I mean, which in this case, it's not very easy. But if you're thinking in terms of memory, like the concept of reading a string from left to right and deciding if by the time you get to the end, if you had the same number of A's and B's. I think if you think about strategies for doing that, it becomes, it's an idea that you might have to say, as I read, I'm going to keep track. Are there any extra A's or are there any extra B's? And the way to store that information in a stack is to have one stack symbol which represents extra A's and another which represents extra B's. I mean, this seems like kind of out of left field, but this is a standard trick. And if I wanted to modify this to say there are the number of A's is 2 times the number of B's, then I would do something like every time I see an A, I push 2 X's, or maybe the other way around. Something like that, right? You modify the way that you keep track of these things to make it equalize at the end. So this is another unsatisfying answer, but the answer to your question is basically this is kind of the whole trick, is to come up with a strategy for doing this. All right, we've only got a few more minutes. I thought I wanted to have you guys try something. Using this stack machine here, could you give a derivation to demonstrate for the string ABB ABA? Show that ABB ABA is accepted using those rules. I didn't give them numbers, but if you like, I'll number them. I'll give you a moment. Oh, we're going to go in a moment. Can we talk about it? I see some people still writing. But actually, if you're doing this correctly, I think there's actually no choices to be made. You basically only have one thing to do, except that epsilon rule, you should save it till the end. That's the grand finale, is doing the epsilon, in this particular one at least. So I did, first of all, the rule 1, right? And now to read a B with an X on the stack, I must do rule 5. So it now says BA, BA, and I cancel that X off of the stack, and I just have S again. All right? And then I read, I don't know what number this is, but the next step should go ABA and then YS, because I read a B, and I put a Y on there. Next I read an A, that should cancel the Y, so it will become BA, S. All right? And then I basically do those same 2 steps again. B reads and becomes a Y, and then I read the A and cancel the Y, and it's now epsilon comma S, and then I do finally the epsilon rule at the end. Epsilon, epsilon, Hey, hey! It's kind of satisfying to me to get the epsilon, epsilon. I really feel like, yes, I killed that word. I murdered those strings. And they're all epsilons now. All right. I think that'll do it for today. I got a few more examples for next time, though. Let me know if you have homework questions. I'm happy to chat. Yes. About this? I'm going to turn this off, and then I will be happy to talk.